All right, so. That out of the way. Let me say a couple of words about the next homework. So I promise you this problem, we actually did this, for a more general thing. I think you can almost sort of rip off what we did for this first problem. We showed actually, earlier in class that R is an Noetherian ring if and only if every prime ideal is finitely generated. Oh, and I wrote this wrong. I'll fix this. Sorry about this. Show that R is a PID if and only if every prime ideal of R is principal. That's what I mean to say here. I'll fix that. Sorry about that. Number two, let PI be a chain of, this is a theorem that we saw in class, so this is you just filling in the details. A chain of ideals in the ring. Show that the following ideals are also prime. The intersection of the PIs and the union of the PIs. Notice this was always an ideal. This was only an ideal because it's a chain. Number three, this is another theorem we had in class. So 2 and 3 are kind of filling in some details here. Show that if R is a commutative ring of 1 and I is a proper ideal in R, then there is a prime that is minimal over I in the sense that I is in P and there's no other prime properly contained between I and P. This doesn't have to be unique, but there has to be at least one. This will come in handy, and you might have to use Lorentz limit to extract a maximum chain of primes. Finally, number four is popularly known as Wilson's theorem, although I think the statement of the theorem predates Wilson's proof by 800 years or thereabouts. Let n bigger than 1 be a natural number. Prove that n is prime if and only if n minus 1 factorial is equivalent to minus 1 mod n. How many of you have seen this theorem before? Okay, right. This is kind of a warm up, I think, toward, because we're after we finish up some more details, we're going to start getting into the integers and some of the number theory stuff, preliminary number theory stuff. Okay, any questions?
In two, those are supposed to be all prime ideals, right? This is a chain of ideals. They're all.
Did I not say prime? I will check that and I will make sure that I say prime, but yes, those are prime ideals in that problem. Yeah, I'll fix that after my second class. Yeah, it's funny because I must not have been thinking I wrote that because I didn't even cut and paste that. I understood it as I cut and paste it, but I didn't. So losing my mind. All right. Okay. So let's pick up what we kind of left off. So the last thing that I think we were talking about was I defined what power series were, which is probably hopefully familiar to you all. And then from that, we defined polynomials. So my definition was sort of module theoretic in a way. Let me go through some. Results here. So there are. This is this is popularly known as the basis theorem. If R is Noetherian, here R, let me say commutative ring of identity. I'll make a remark after this. If R is Noetherian, then so is Rx. I've proved that to a number of you before, so maybe I'll give that a miss now. However, if anybody wants to see the proof of the Hilbert basis, then I'm more than happy to go over it with you. So this is a big, big theorem, and this is what makes a lot of theorems, especially in computational commutative algebra, kind of cool, because when you start with R and all its ideals are finally generated, this persists in polynomial rings, right? If this weren't the case, things would be much more amiss. Here is a remark, kind of a supplement to this, which I've always found kind of interesting. In fact, so is the converse true. That is to say, if Rx is Noetherian, then is R. The answer is yes, but even more strong. In fact, if Rx is Noetherian, then R is Noetherian with identity. So this converse is strong. So if you start off and you say, okay, R, I'm going to assume it's commutative, but maybe I'm not even assuming identity. If Rx is Noetherian, that forces the ring to have an identity, right? This is kind of surprising, right? Because you get the identity for nothing here. And let me kind of sketch this out. Why is this true? And so whenever I bring this up to somebody, I say, you know, go look in your favorite book or ask me to prove the Hilbert basis theorem and ask yourself. So what this theorem says is if R doesn't have identity, then Rx is never Noetherian. That means somewhere in the proof of the Hilbert basis theorem, you have to use the fact that the ring has identity. And if you look in Hungerford, if you look in any place that looks at it, it does use that fact, but it's subtle. It's very subtle. So here's an example. 2z is Noetherian. In the sense that all its ideals are finitely generated, right? Because in fact, look, it's a cyclic group, right? However, 2zx is not. So if it's not Noetherian, there must be an ideal that is not finitely generated. Anybody see one? So let me be careful about this. This is the set of, let's say, n0 plus n1x plus n2x squared plus nm xm such that ni is in 2z is even. Anybody see the ideal is not finitely generated?
6x 10x squared 14x to the third, just basically keep on adding primes and raising the power.
You'd be like 2x squared, 2x.
That's easier to see, I think.
Okay.
In Zx, this is the ideal generated by 2. But there is no x. This ring has no x. It's got 2x, it's got 4x, but there is no x. So 2x is not actually a multiple of this because there is no x to multiply that. Right? 2x is kind of an independent element. Same here, right? I mean, it's subtle, right? But when you have a ring without identity, you don't have the x. You just have crap from R that's kind of glued to the x. There is no 1, right? So you might think about the details on that one. But I always find that kind of a fascinating example. Theorem. If R is Noetherian, again, we want to communicate with identity, then R power x is there. the proof of this is actually very different from the proof of the Hilbert basis theorem. But this is kind of a good thing to know. Both Noetherian is a very strong finiteness condition. All ideals are finitely generated. This is preserved both in power series as well as polynomials. Liquid on it.
Someone's sabotage.
Yeah.
Is it just the marker or is?
Maybe it's a custodian. So, if R is a domain, then the element X is prime. And it's if and only. What's that now? Yes. Proof. Consider phi from Rx into R, doing, I think, what you think would come naturally. Phi of f of x, input your polynomial, is f of 0. Notice that this is clearly, I hate when I say clearly, but I think in this case it kind of is. This is an onto homomorphism. But certainly everything in R is in the image of this, and it's evaluation of polynomial with a fixed number of homomorphism. Everybody okay with it? The kernel of phi. Well, the kernel of this is just all polynomials that have 0 for a constant term. So this is the set of x, f of x, which is, of course, the ideal generated by x. Therefore, Rx modulo the ideal generated by x is isomorphic to R, which is a domain. So the ideal generated by x is a prime. Weird things can happen if R is not a domain. This example always kind of makes me a little angry. In D6x that's enough to kind of make a body angry, right? Because in Z6x, part of this is 6x squared, which is 0. And the constant term is also 0. And the linear x term is 9 plus 4, which is 13, which is 1. Right? So x, which you used to being prime, x isn't even irreducible. Right? Okay. So let me see. Definition. If f of x is let's say AM XM plus AM plus one, XM plus one plus AN XN. Notice that I can consider this both to be a polynomial and a power series. Then degree of f of x is equal to n. The degree for a typical element of a power series ring is usually not defined because there may be no n, it could go on forever. And the order of f of x is n. Typically, the degree is what we discussed for polynomial rings because it always exists. And the ORD is what we discussed for power series rings because that's the one that exists there. But let me do the following theorem here. So theorem, let R be the domain and FG be an R of X. You guys need to read this.
That's some weird shit.
Now it's like it's like when you that's what I thought it was just a kid. And if you ever got the yellow anywhere near black.
Yeah,
it
yeah.
ruined it for them. What's the date?
So do you know,
I literally just
and somebody quote clean this board?
They usually bring it.
I mean, it looks like along the bottom there.
You know,
it could like the fact that it was like.
Yeah, it looked like, I mean, it looked like the
And it
the stuff where I haven't written.
That's my theory.
I mean, there's definitely
Mention
streaks all over it, like along the bottom.
Well, they didn't do something. So let me see if this works. If you look at one degree of what is true about this?
The maximum of 2 degrees.
It's plus or equal to max, right? Of course, if they, and in fact, it's equal to max if the degrees are different, right? And even if the degrees are the same, it still could be the max, but it's possible they cancel out. And if you're a domain, the degree of the product is just the sum of the degrees. We've seen an example earlier where this certainly doesn't necessarily happen when you're in a domain, because some of the degrees here is 2 and the degree of the product is just 1. If F and G, if we consider this, and of course, if they're in the polynomial ring or the power series ring, this can work for any power series. Or what happens now?
It'll be greater than or equal to
It's greater than or equal to
the max.
men. right, and two or FG is equal to, yeah, and again, ours domain is or F. Plus or. And to make this, well, to make this, hold up, I guess, how would we have to define the degree of the zero polynomial? Well, one of the things that we could do is we could state this theorem by saying, okay, assume that F plus G is not zero, right? But, how could, what can we do to make this compatible? How can we define the degree of the zero polynomial?
The degree.
I think you want it to be negative infinity, actually. Alright, and how about the OR? That only you'd want to be infinite. Right? Okay, so as a corollary, there's a bunch of, so here for degree, there's a bunch of nifty corollaries. I'm gonna put this all together in one corollary. Let if R is a domain, then Rx is a domain. And U Rx is equal to let me talk you through this really quick. If R is an integral domain, then look at Rx. If you multiply two polynomials in Rx, and get zero, that means that, well, this thing right here, yeah, this is for domain. The only way that you can get zero is for one of these to have degree minus infinity, which is one of them being zero, right? That's one way to look at it. And how about the unit? Oh, and also I guess I should throw in that if integral domains have to have the identity, but the identity of the polynomials is the same as the identity of the ring. How about the units? Well, certainly the units bar contained in the units bar X, right? Now, if you have something that's a unit in Rx, ask yourself, what can its degree be? Because FG is 1, which has degree 0. So if this is degree 0, that means both F and G have to be degree 0. And so your only units have to be downstairs in R in the first place, right? By the way, what does a unit
Constant term.
okay, that's true. So it's like this.
That's supposed to be power series or bond.
What's that name?
That's power series or bond.
No, polynomial.
Just
We already just.
So that's just what you wrote up, just about.
In general,
so not in a
are
domain.
not domain necessarily. So this is, when I say in general, I mean perhaps R has 0 divisors.
So plus and no problem.
That is correct. So more generally, it looks like this. The beginning is a U and R, and every other term is nilpotent. So in fact, this formula persists not just in domains, but actually in reduced rings where there are no non-zero nilpotents. If all the nilpotents are zero, you get the same. Any questions? So let me also point out that for power series, I'll make this remark here. For our power acts, when R is a domain, X is prime. And just like the polynomial, this does depend on X, or I'm sorry, R being the domain. And so our power X is a domain. So if R is a domain, so is the power series ring. The first sort of deviation from what you're used to is here's the here. Actually, I just need that. But R being a community room identity. You don't even need the name here. So what do the units look like here?
That was here.
All right. This is the f of x such that f of 0 is in. So it's basically all power series you can form. A1 x A2 U units and AI in R. This is very different from polynomials. So, for example, one plus x, for example, is actually, let me make my life easier. Let me say 1 minus x is not a unit in R. However, and you know what's one of the coolest things about algebra is at this point, I do not have to write absolute value of x is less than 1, right? Because we're just pushing around symbols here. Okay. Why is this true? Well, what you can do to verify this is you can inductively build. So if you start with actually one direction is clear, right? Right. Well, one part of this is true. If you have a unit, then certainly the constant term has to be a unit, right? Y is anything that looks like this a unit is a kind of interesting proposition. Let me point out, so I'm not gonna give a formal proof, but I'm gonna do something a little bit fast and loose, but hopefully will give you the idea. Y is u plus a1x, a2x squared plus a unit. It is clear that any unit must have this form because it has to have constant term this, but why does everything in this form have to be a unit? Well, I'm going to simplify this first and notice notice this thing is a unit if and only if multiplying it by another unit is a unit. So I can make my life easier by saying, if I want to show that this is a unit, I'll just multiply this by u inverse, right? And if what I get is still a unit, then all I have to do is kind of unwrap my package. Everybody clear on that? And so why is this a unit, right? Well, now I've got it a little bit easier because it starts with 1. And so this is like totally sloppy, and I'm embarrassed I'm recording this, but I'm gonna do it anyway because it's not a formal proof, but I think it will give you an idea of how you build the next term. Right, I feel like I'm in 4th grade again, right? But so this is 1 plus b1x, b2x squared plus b3x cubed. And what do? You subtract, right? So we've got two things working in our favor, and I'll point the first one out now. What do I have to do now? I have to find the appropriate thing that will kill this b1x, and 1 makes my life easy. All right. So this is b1x, and this is b1 squared, x squared, and this is b1, b2, x cubed, etc. Let's see, did I do this right?
B minus B.
Yeah, it should be minus. I need to make it match, don't I? Minus. So yeah, it should all be minus. And now again, I subtract. This is dead, and I've got the next degree. So what I have is b1 squared minus b2 x squared plus b1 b2 minus b3 x cubed, etc. And again, with the 1, I can make this match, right? This now needs to be plus b1 squared minus b2 x squared. And this gets to be more and more of a mess. And this is b1 cubed minus b1 b2 x cubed, etc. And I keep subtracting. No matter what is spit out at the next step, this is a 1, and so all I have to do is just take that thing and put it in, and it'll be bigger and bigger every time. Everybody agree with that? That's key 1. That's the unit part working for me, because no matter what comes out as a leading term, I can just multiply, divide it by 1, and I just reproduce it there. And here's key point number 2. I never have to stop because it's a power series, right? And so you just keep going, and you can inductively show that this thing is actually the inverse. How would you do this more formally if you care to do so? Well, you start off with, actually, I probably would start off with 1 of this form, but in general, what you do is if you start off with u, then the first if you're gonna try to show that this is unit, obviously the constant term of the other one has to be U inverse. Right, and that matches, then you find that U1 basically doing this, or you find the linear coefficient that makes this cancel. And then by induction, you've got it up to n, and then just show you build the n plus one, and again, the unit's gonna help you do that. Right, so this is basically the idea. What this means is, for polynomials, your units basically correspond to what you get in the original domain, right? So with something like z, right, if you look at zx, still the only units are plus one, minus one. Now take zx and add another polynomial variable, still just plus and minus one, et cetera, right? In fact, you can go on forever that way. With power series, your unit group is always uncountable, always. Right, because you've got complete freedom. In fact, you've even got uncountably many just to perform this, because even if your ring only has two elements, which is the smallest ring I can imagine that has an identity, then this is even with something like F2, then this right here corresponds to base 2 decimal expansions, right? Which is in one-to-one correspondence with the interval 0, 1. Right, so the unit groups of these power series rings are very, very large. Okay, any questions on that? Let me give you another example real quick. Here's one corollary to this. Yeah. F is a field. We just mentioned these cases a moment ago. Then F power X is a local PID. So you all know what PID is. It's only got I hope I define this when I talk about localizations. But a local ring is one. Well, actually, the terminology local also usually refers to the theorem as well. We're okay because it's PID. Local means it's got only one max quantity. Let's prove this. In fact, yes.
So what does that have to do with localization?
Well, because when you take a prime ideal in a ring, and you take a prime ideal here, P, if you look at R localized P is that construction right there is always has a unique maximal ideal. And in this case, because the prime ideals of R localized at P are in one-to-one correspondence with prime ideals of R that contain P. So there's only one maximal ideal here, and it's PRP. I say quasi-local because it's not necessarily in the theorem, but this construction always gives you a ring that's only got one maximal ideal. In fact, this is stronger than a PID. Anybody know what this is?
Valuation.
That's too strong. Yes, you're right. It is correct. It's actually a Euclidean domain. So proof. Let me prove that it's Euclidean. That'll be fun, won't it? Let f of x and f power x be non-zero. Right, I mean, the zero power series is silly, so I'm gonna ignore that for a while. So what do I know about f of x? Well, if it's not zero, it has to have a non-zero term in it. So I'm gonna start with the lowest one. I don't know much, but I know this looks like am xm plus am plus 1 xm plus one plus forever with am not equal to zero. So I'm basically, I've isolated the lowest term, and of course, the ord of f is equal to m. Now, check this out, nothing up my sleeve. This is x to the m times am plus am plus one x plus am plus two x squared plus blah, blah. Am is not zero. And so what can you say about this? It's a unit because f is a field and this is a non-zero element. So this is a power series that starts with a unit. It is a unit. Right? There's a nifty conclusion that we can come to for all this. Conclusion. If f of x is in f power x, and let's say not zero, then f of x is equal to x to the m power times u, with u a unit in f power x. Right, okay.
For this corner, is, you said a local community is has one maximum.
Yes,
So in this case, it's the maximum ideal like this X. Like,
actually, the maximum ideal will be the ideal driven by x.
okay,
Right, so, actually, we're gonna see that Adam was right about his remark about valuation domains, which I haven't defined for all of you yet, we're gonna talk about later. But what does it mean to be Euclidean, right? It means that there is a function. So there exists a function phi from f power x not zero into the natural numbers union zero. That satisfies a couple of things. One, phi of AB is greater than or equal to phi of A. Actually, you don't really need this condition, but I put it in there because it's popular to do it, and I do want to be popular. So, well, you've got this condition, and you've got the Euclidean algorithm condition, which says, given A, B, and the whole ring, such that B is not zero, then there exists Q R in f power x such that A equals Q B plus R with R equals zero or Euclidean algorithm basically says there's a division algorithm where you can always get small remainders. So what this says is if I give you two random elements in the power series ring, where this one's not zero, I don't want to try to divide by zero, then I can divide A by B, giving a quotient of Q and a remainder of R. And either R is zero, so B completely divided A, or the size measured by this little Euclidean thing, the size of R is less than B. So I've got this down to a remainder that's smaller than what I divided by. Right? Now, here's the scoop. And actually, I want to assume they're both not zero just to make it easier. Because if A equals zero, then certainly B divides A, right? So no problem there. So I'll assume these are both zero. So A is, let's say x to the n times u, and B is x to the m times u. not one, say D. Where U, V are in the units of power X. And M, N in the natural numbers union 0. Now, I am going to attempt to divide A by B. Let me know if M is no more than N, then we can take Q to be whatever A divided by B is, which would be X to the N minus M UV inverse. And now when you notice when you multiply Q times B, you get X to the N U, which is A, right? And so in this case, R equals 0. So it works. What do you suppose happens if this thing is actually bigger than N?
Q equals 0, R equals.
In this case, what I would do, X to the N U is 0 times X to the M B plus X to the N U. And I didn't tell you actually, I feel like kind of a tool here, but so what do you suppose the function here is on X to the N U? What's the size function? Right, it just measures the order. Right, so you just measure the order. There you go. So notice in this case, what happens is here, this is A, Q, the quotient is 0, and the remainder is just divided by. And notice that B of R is, in fact, in this case, N, which is less than M, which is B of B. So this is a Euclidean domain, so it's a PID. Why is it local? Let me point out the ideal generated by X in F power X is maximum. So let me, the justification for this is when you take F power X, be multiplied by the ideal generated by X, you get F, which is a field, right? Which shows that this ideal is maximum. But now the question is, why is this the only maximum ideal? Let N be another proper ideal. Any proper ideal you want. Right? And Z and N a non-zero element. Any non-zero element. But Z is of the form X to the M times U, which is contained in the ideal generated by X. Therefore, every single proper ideal in this domain is contained in this maximum ideal here. So X is unique among the collection of maximum ideals. Okay, any questions on that? Yes.
Could we say that M can't be zero because otherwise, obviously, the N wouldn't be proper? Like M can't be zero, C can't be a unit, otherwise N.
Oh, so you're worried, so you're worried about my assumption here that N is a non-zero ideal? Is that,
Right, I'm just saying,
I think he's saying the exponent M.
the exponent M cannot be zero because then it would.
oh,
be
right,
unit, which
because
would-
C is an element of a proper ideal.
Right.
Right, exactly, and, you know, maybe, yeah, another thing is, let's assume that this is not, zero. That's probably, I should have probably been good at doing that, right? Because if it's zero, you can't represent it in there, but of course, zero is clearly in any maximal ideal that I want. Okay, good, any other questions? Yes,
This may be a little out of scope, but like, I have a question about like word local. So I know like in algebraic geometry, like maximum ideals correspond to like say, you have some coordinate corresponding to some priority. They correspond to like points
Mhm.
on the ideal, so you are like getting some like local data.
right.
So is that like a nice coincidence or?
No, that's one can argue that that's where it came from. It's localization technique, you kind of look at curves at a point, and you get a local range. The terminology that's used in my branch is usually local means quasi-local, which means unique maximal ideal, plus the Noetherian condition. But some people just use local for anything that only has one maximal ideal. I use the terminology quasi-local for something that only has one maximal ideal. And if I say local, I mean it's also Noetherian. Okay, other questions? All right, well, you all, no math club today, but there will be one next Friday. Have a good first Friday, and I will see you all by Monday.